And I think we should begin this lecture. I'd just like to say welcome. And this lecture is part of the course PE 531, which I'm teaching, Statistical Learning Theory. And I've been using a textbook, Understanding Machine Learning, from theory to application. And today we have an author of the book. This is to the students who are taking PE 531. The project is out. We have a list of papers that you need to select and review. Okay. So let me just tell you a little bit about the author who will be presenting today's lecture. He has a background in math, physics, and psychology, and he's been working on machine learning. I would say more on the theoretical side. And the way machine learning is going right now, it's leaning more towards application. And I think that we're sort of forgetting the importance of machine learning theory. So it's a great pleasure to have our guest today to talk about theory. And today, last week, we gave us a wonderful talk about estimating or approximating or learning the distribution. Today, he's going to be talking about another very, very important topic, fairness in AI. AI, or fairness in machine learning. Machine learning algorithms are used to make decisions on various tasks. And we depend on that decision. And if that decision is biased in any way, minorities, people with, with disabilities, for instance, will be injured or will not be, will be discriminated. And today, our speaker today will talk about this very important issue about fairness. So let's give him a warm welcome to the podium. Thank you.
I'm going to talk about fairness in machine learning decision making. Thank you for the introduction. I think my first slides kind of repeat what you were saying. So we know that there are lots of breakthrough in machine learning, and something which, I mean, when I started working on it in the late 1980s, it was a very theoretical issue, but now it's widespread and it became a public concern, so we know that corporate research and AI startups, they use machine learning all over. They use machine learning to guide decisions in criminal justice. I know that that's the situation in the US and North Korea. I know that a lot of people use machine learning to choose among applicants for a loan in a bank. We use it to filter candidates for university programs. And we use it in health science, diagnostic. So many applications of machine learning. And the issue is that machine learning systems are typically trained to estimate conditional probabilities. So what the system is optimized towards is being able to predict a label given an instance, to optimize this conditional probability. But we use them in a different way. We use them to guide actions. We use them to make decisions, which is different than predicting the label given an instance. So there is kind of a leap between what the model predicts and doing real-world applications. So the question is, what should we require for machine learning tools beyond the accuracy of prediction that that's what they are trained on? So there are lots of kind of other considerations that we want to take into account. One of them is fairness, the other one is explainability. We want that our decisions will be justifiable, people will understand how we make a decision. We want trustworthiness. We also want our decisions to somehow improve social good. So there are lots of goals which are not just correct predictions of a label or probability correct prediction. And the question is, how do we handle machine learning to those new considerations that are not part of the basic tools that we develop. So one thing I want to mention is that it's often the case that we use machine learning tools to infer causality, to understand why something happened, what caused it. And I want to kind of warn, I mean, I'm not going into causality now, but just a warning. I mean, causality is a very complicated issue. We can model it mathematically based only if we base on very strong assumptions. But what happens in practice is that machine learning is being applied to kind of conclude causality conclusions in the hope that those assumptions hold, but without any justification that the assumptions really hold. So I think we have to be very careful when we try to use machine learning tools to infer causality, because the only way we know how to mathematically handle causality is by making very strong assumptions, and those assumptions usually don't hold in practice. Okay, but I want to focus in this work on one aspect of those extra considerations, which is fairness. So let me start by giving you a few examples. I want to appeal to your intuition about fairness. So I'll give you a few examples, and just we want us to bear in mind what do we consider fair in those practical examples. So my first example is a very famous case. There is this COMPASS program. COMPASS stands for Correctional Offender Management Profiling Alternative Sanctions. It's an algorithm that is a commercial algorithm used in the US in the court system to predict the likelihood that a defendant will become recidivist. That is, you have someone who is being accused of some crime, he comes to court for initial hearing, and they have to decide whether to release the person on bail or to keep them in custody. And they use the system to try to predict whether this accused person is going to reoffend during the release period. And when you look at we can look at the predictions of the systems, and then they release them, and then we can see whether they re-offended during the time between the discussion and the next meeting of the trial or a year. And what the model predicts, it turns out that 45% false positive when they try to predict recidivism for black offenders, compared to only 23 false positive for white offenders. So it means that when the system predicts that someone will re-offend and they are black, then 45% of the time they are wrong. This person is not re-offended. But when it's a white person, they are wrong only 23% of the time. So is this unfair? Is this unfair to black people? Because we are more often, more likely to predict they are going to offend the law again when they don't, compared to what happens with white people. So that's one case just to bear in mind. Is this algorithm unfair? And this has been a matter of discussions and court cases and so on. Here is another case. So we know, this is data from the Ontario licensing office. A female 17 years old in a driving test candidate is 7% less likely to pass the test than a male candidate of the same age. So if you go to the driving test office and you check how many passed on the first test, then young male are more likely to pass the first test. And when we go to the age of 50, the difference between female and male goes to 50%. So now, with the driving school, so say it's a driving school, and I'm sending you a package that say you have a fixed sum until you pass the test. Will I be unfair if I charge more according to age and gender? Will you consider it to be unfair? Because I'm giving you a fixed charge until you pass the test. And I know the statistics. But now I am publicizing different prices to different genders or to different ages. Am I being unfair? Here is another example. The Ontario Student Aid Program, it gives 95 of its grants to students whose annual family income is below $80,000. Is this unfair towards students that come from rich families? So, and I'm not asking for an answer, I just want to raise your awareness that this is a complicated issue. And we are trying to address it formally and trying to define and try to give precise answers to these complicated questions. Okay, so let me try to formalize it, and then we can discuss it more precisely. So I'm looking at a situation where we usually consider machine learning. So you assume that there is a generating distribution that generates data, or it's the distribution of customers. And this is the distribution over X goes Y, where X are the features of the person that I'm trying to predict, and Y is the label, say +1, -1. Pass the test, will not pass the test. So on top of it, assume that we have two groups of customers, say I denote them A and D for advantage and disadvantage group. So that's our basic setup. So it's a usual setup for statistical learning, but I added this distinction between two groups. Okay, so now we have a predictor. A predictor is a function that takes a customer and predicts whether they will pass or not pass. And so the customer has a label Y, and the true label whether he pass or not, and I denote by Y hat the prediction. I'm making a prediction whether they will pass the test or not, and Y is the true label whether they passed or not. So often my prediction is not a function to 0 or 1, but often my prediction is a score function. I give every candidate a score of kind of their likelihood, what I think is their likelihood to pass the test, and then I use some threshold and I turn it into a prediction of a label by thresholding this score. Okay, so all these are very basic machine learning. So now we define the accuracy of my predictor F as the expected over customers and their labels that my prediction y hat equals the true label y. So far, everything is completely standard, basic statistical learning, and then we can talk about these four subsets of the population. The true positives, so you see here, I predicted that the label is 1 and the label is indeed 1, so that's true positive. Here I predicted the label is 1, but the label was -1, so it's false positive. This is false negative and true negative. That's all very basic. And based on this, we're going to try to define fairness. So the true positive rate, just to remind you, true positive rate is the number of true positive divided by the number of the true positives divided by the true positive for the false negative, because false negatives are also positives. So the false positive rate is how many did I predict positive among all those that are really positive. Okay, so that's our basic setup. And now we can try to think about notions of fairness. So the first and simplest notion of fairness is statistical parity. So what does statistical parity tell you? We want that the probability that I predict label 1 for customers in group A is the same as my probability that I predict 1 for customers in group B. So I have the same percentage of predicting 1 in both groups. So the same probability in both groups, same acceptance rate over the two groups, or same rate of giving a loan between the two groups. So what are the advantages of such a notion of fairness? Clearly, it is very easy to evaluate. I don't need to know whether you passed the test or not. I don't need to know whether you returned the loan or not. I just count how many people did I give a loan in group A, to what percentage of the people I gave a loan in group A, to what percentage of the people I gave a loan in group B, and in group D, and I want them to be the same. So it's easy to understand, no need to have statistical sophistication. But of course, there are downsides to this simple measure. Because this simple measure, it will help accuracy whenever the true classification is correlated with the group membership. Right? For example, by this measure, the driving tests are not fair. Because the driving tests do not give the same percentage of pass to men and women. They do not give the same percentage of pass to 17-year-old male and to 70-year-old women. So they fail this statistical parity. But we know that there is a correlation between the group membership and your success rate. Okay, so the problem is that this is a very simple measure, very easy to do mathematics with, very easy to explain to judges, very easy everything, except that it is go against accuracy. The minute there is a correlation between the group membership and the feature that we are trying to predict. So let us look at some more subtle notions of fairness. So the next notion of fairness that we want to consider is equalized odds. So what does equalized odds say? It says that the probability that I will predict 1 among all of those that are deserving and belong to group A is the same as the probability that I will predict 1 among those that are deserving and belong to group D. So now I do take the true label of the individual, whether they are deserving or not, and I want to just, among all those deserving, I give the same percentage of success to those in group A as to those in group B. So that's kind of takes the true labeling into account and allows me to consider correlation between the group membership and the success, the true success, or the true label of the person. So let's say that the true positive rates are the same in both groups, and similarly you can ask that the false positive rates are the same, so that those that I accept by mistake are the same proportion of accepting by mistakes in group A and the same proportion of accepting by mistake in group D. So that's what we call the notion of equalized odd or equal opportunity. And the pros is, of course, it sounds very reasonable. We take the success into account. Among all the deserving, I give success to the same percentage in both groups. And it is kind of desirable from the applicant point of view. From the applicant point of view, you know that if I deserve to get accepted to this program at the university, my chances of the university will accept me do not depend on whether I belong to one group or the other. So from the point of view of the applicant, it's very nice, but still there are issues. The first issue is very hard to evaluate, because how can we stand in the decision time, I want to give you a loan, I want to get you to the program university, how can this measure depends on your true labor. So when I'm giving you a loan, I don't know whether you are someone that will return the loan or not. I don't know what your true labor is. So it's very difficult to evaluate a decision time. Another problem is that, and that's a real problem, it may be confusing to non-mathematicians. If someone is trying to claim at court that he's been disadvantaged and treated badly, sometimes this kind of conditional probability is difficult for the judge to understand. So, but that's kind of more sophisticated, and in some sense it gives us a feeling that it captures better what fairness is. And it looks like, oh, we have a solution. But let me show you another option. Another option is predictive parity. So what am I asking now? I'm asking now that the probability of successful candidates among those that I accepted will be the same in group A and in group B. So you see, before I asked that among all the deserving, I accepted the same rate. But now I look at those that I accepted, I look at those that I accepted, and ask which percentage of them were really successful. And I want that to be the same in both groups. This also sounds very reasonable. I look at those that got the loan, and then I see what percentage of them returned the loan among group A and among group D. So that's what the compass was failing in our example. We looked at those that were predicted, among those that were predicted to reoffend, we looked at the percentage that really reoffended and compared it between the two groups. But you see, this is also a very intuitive notion of fair. Among those that I accepted, I want to have the success rate the same in both groups. If among those that I accepted, I see that the success rate of, say, women is higher than the success rate of men, it means that I was too lenient in accepting men compared to how strict I was in accepting women. I only accepted women that are really successful. So this could be a very reasonable notion of fairness. So this also sounds right, it is intuitive, it is desirable from the point of view of the university. The university wants to know that among those that I accepted, the rate of success is the same between the two groups. You see, the other one was desirable from the point of view of the applicant. Among those that are deserving, my chance of being accepted is the same. Here I'm saying among those that I accepted, I'm the university, the success rates should be the same. So that's kind of desirable from the point of view of the granting agency. And the cons is, of course, it's hard to evaluate. I mean, you see, I have to evaluate what would have been also the success among those that are rejected. Among those that are rejected, I have to know who would have succeeded, but I don't know it. So it's very difficult to evaluate. And it's similarly confusing to the non-mathematician to regulate. And the funny thing is that these two requirements cannot be met simultaneously. So you would like to say, oh, the first one sounded very reasonable, that's a good definition of fairness. The second one also sounded very reasonable, it's also a good notion of fairness. But we cannot satisfy both at the same time. So the Compass Company, when they were telling it, you fail this second criteria of fairness, they showed that they do satisfy the first criteria of fairness. It's like this Jewish joke about people having a dispute. They come to the rabbi to decide, and the rabbi is listening to the first person, and the first person explains why he is right, and the rabbi says, you are correct, I'm with you. Then the other person says, oh my God, just a second, you didn't hear me at all. So the rabbi says, oh, I'm willing to hear you too. So the other guy argues and says, oh, you are correct. So now both of them jump up and say, I mean, how can you say he's correct and I'm correct? So the rabbi thinks, yes, you're correct. So there's a situation where we are now. We have two criteria. Now each of them sounds reasonable, but they contradict each other. The only case where they will not contradict each other is if the success rates, the true success rates between the two groups will be the same. If the success rates between the groups is the same, then all the notion of fairness becomes trivial and we don't have to worry about it. We just can worry about predicting success. So this is the theorem. This was shown in 2017, but there are many results that showing this kind of very simple observation that if the success rates differ between the two groups, then predictive parity is incompatible with equalized group. These two measures cannot be made simultaneously. You have to pick which one you prefer. And it's very difficult for the university, for the banding agency, for the regulators to decide which of them makes more sense. I mean, people make regulations. The European Union make a regulation say you must be fair in accepting students to programs. But the regulator, the person who sits in the parliament, doesn't have the tools to tell which of them makes more sense. Most of them make sense, but you can't satisfy both of them. So, how can we rectify it? Assume that you found out that your measure is not, I mean, you see, you have a tool of predicting, accepting students to university. So you use the tool, you accepted students. Now you look at your cohort of students that you accepted 3 or 4 years ago, you look at the success, and you realize that you were not fair, that you had more false positives for men than for women. You accepted more failing men than you accepted failing women. So how can you rectify it? So this paper in 2016 showed that there is an optimal way to fix it. What is the optimal way to fix it? It is to add randomization. So what happens is that the optimal way to fix it is to add randomizations that depend on your group membership. I can fix it by saying, okay, you see, I got a higher rate of failures among men that I accepted than among women. So what I will do is when my program tells me you should accept these men, I will flip a coin, and if it falls head, I will reject them. And if the program tells me accept this woman, I will also flip the coin, but with a different bias. I will have my coin that has a chance of rejecting a good candidate higher for men than for women because it wants to compensate for this injustice. So the optimal way to fix it is by flipping a coin that is biased according to group membership, which you can argue, is this fair? that if you are a man, then I flip a coin that kicks you out, although you are deserving, kicks you out with probability 20%, but if you're a woman and you're deserving, I don't flip a coin. I flip a coin that kicks you out only with 5%. Is that fair? But provably, this is the optimal way to fix the unfairness that we saw in our predictor. So what, yes?
So in terms of optimality, what is the criteria you have? Because you said that.
Oh, okay, so you can say that based on, I mean, I don't want to get into the exact definition, but based on the data that you have, there is no other algorithm that will get you better fairness outcome.
We have different definitions of fairness.
Right, no, I'm talking here about the equalized odds. But you have the same results for the equal opportunity. So no matter what your notion of fairness, you realize that you are not fair, and you ask what algorithmic tool, based on the knowledge that I have, will give me optimal fairness. And it turns out that the optimal fairness that you can get without adding more knowledge is just by flipping this biased coin. So what I'm saying is that the situation is difficult. We have conflicting notions of fairness, that both of them make sense, and furthermore, if we try to correct it, we are obviously doing something which is not fair. And we can say maybe there is a different solution, and here is another solution, which is individual fairness. So individual fairness was presented in the original work in 2012 by Dwork et al. That started this kind of called our attention to the issue of fairness in machine learning decisions. And so they defined individual fairness, and they defined it in very vague terms. They say individual fairness is that similar individuals should be treated similarly. But of course you can jump and say, what are similar individuals? Like, am I similar to you or not? And does it depend on the shirt that we are wearing? So, of course the question is, how should we define similarity? And their answer in this paper is a hypothetical, task-specific metric. So, we don't know how to define this similarity, but it should be a similarity that is task-specific, and it determines the degree in which similar individuals are likely to succeed at the task at hand. So, in some way, this solution says, you don't know what fairness is, I will solve your problem. Let's call it similarity, and someone else will have to worry about what similarity is. But we don't have an answer to what is a good similarity notion. Okay, so I can go more into this. I mean, I have lots of things that I wanted to cover in this talk, so I will not go further into individual fairness. There are several issues with it, but instead I want to talk about how it compares to the notions of fairness that we discussed before. I already spent time convincing you of two other notions that make sense. Here is a new notion, how do they compare? So, regardless of the challenge of finding this similarity notion, there is a fundamental conflict between this kind of individual fairness and the group fairness. So this is real data. This is real data in some county in California. And what we have here is the histogram of the probability of reoffending of people that appears in court. So what we look here is that for white offenders, you see that you look at the probability of reoffending, and you look at the height here is how many are reoffending, right? So among those most of those that are reoffending that are in the range of 0 to 25% of reoffending, and the graph looks different for black people. So this is just you look at your population, you look at the people that came to court, you look at the record a year from the appearance in court, and you ask whether they had a record of reoffending within this year, and you see what percentage of them were, I mean, what is the histogram of the population in terms of the chance of reoffending. So it's different between the black population and the white population. You see that in the white population, most of them that did not reoffend, I mean, had low rate of reoffending, and among the black population, a higher part of the graph is here. But now, assume that we are trying to do individual fairness. So I'm trying to say all I care about is whether you're going to reoffend or not. And based on this, I want to make a decision whether I release you in bail or not. So what I do now, to be completely fair, I don't look at your race at all, I will give a threshold. And I will say, assume that I knew your probability of reoffending. Everybody that has probability of reoffending below 20%, I will release them. Everybody that has probability of reoffending above 20%, I will keep them in custody. That is completely individual fair. Because I did not look at anything else, right? But this is going to violate group fairness. Why? Because remember what we did in group fairness. We asked what percentage of those that I released, what percentage of them reoffended, right? And that's exactly the area under the curve. And the area under the curve for the white people is different than the area under the curve for the black people. So by doing this individual fairness decision, that I just assumed that I had an oracle that told me what is your probability of reoffending in the next year. And I will just do a threshold and I will keep you in custody if you have probability of reoffending bigger than 20%. I don't look at who you are, I don't look at your color, nothing. Very individually fair, but it violates the notions of group fairness that we talked about before. Because the group fairness is, I look at among all of those that I released, what percentage of them reoffended, which is the area under the graph. And I will have a higher percentage of reoffending among the white people that I released than among the black people that I released. So the individual fairness, not only it is not well defined and difficult to evaluate and everything, it also another notion that contradicts the other two notions that already contradicted each other. Do you want to?
Yeah, I just wanted to ask you. So you said you're picking just some threshold without looking at the color of the skin,
Right.
right? And you just chose 20%, and that's individual fairness. But I mean, the notion of similarity. What is the notion of similarity in that situation?
In this situation, the notion of similarity is that they have the same probability of reoffending.
Okay, so the score that they got.
The score that they, and that's the true score. That's a true score because this is backwards data. After I released them, after I waited a year, so I know the true score.
But I mean, so you either go individual fairness or group fairness, and individual fairness is chosen, and
there are lots of problems with individual fairness, and I mean, I can talk about, maybe if I have time at the end, I will talk about issues with individual fairness. But what I wanted to show now is why you can see that inevitably, whenever the groups are different in terms of their probability of success, in terms of the distribution, those measures will contradict each other. Yes?
These are the base rates for reoffending, in reality, not the compass scores?
No, it's not the compass scores.
The base rates?
It's the true rates. It's, you look at the people that came to court, you release them, and you look at the data a year later, and you look at how many of them reoffended. And you look at the history. So this is information that we don't have at the time of decision. This is just in retrospect. But we're just saying, if we were really had a miracle board that will tell us who is going to reoffend or not, and we will use it to do individual fairness, because just look at the success rate. We will still, with this magical future scene, we will still be violating group fairness. So,
So that was based on back data, so you.
yeah, that was better maybe.
Okay.
Okay, so we have a kind of a discouraging conclusion at this point, that our perception of algorithmic fairness is inherently inconsistent. We can convince ourselves of different measures that each of them sounds very reasonable, but they are inconsistent with each other. We are just like this rabbi that says to each of the arguing people that they are correct. So the desirable requirements from fairness, they contradict each other, and even if we try to rectify fairness, we rectify it by introducing more unfairness. So although we seem to have an intuitive understanding of what fairness is, what could be the reason that there is this gap between our intuition and our ability to formalize it? So what I claim is that part of this gap is that when we want to define an algorithm, we need to rely on observable features. But our intuitive notion of fairness often depends on unobservable features. So what I mean by unobservable features? So, for example, I mean, you can ask, does observation suffice? So, I'm going in the wrong direction. Okay, so if we want to be able to scrutinize our decisions, we need to rely only on observable features. But in intuition, we think, how do we decide if something is fair or not? We also take into account things like this, things like causality. Why did I release this person? Right? And I don't know if I told you this in the, probably not. I'm in a recruiting committee of our school, and I'm in the recruiting committee of ECTO. We make decisions of whether to accept someone as a faculty or not. We have candidates. So 2 or 3 weeks ago, we had a female candidate that in her slides, in her job talk, she had something which looked completely fishy. So the head of the committee, when he interviewed her one-on-one, he asked her about it. How come this is a wrong slide? And she could not figure out what was wrong. So we came to the discussion of the committee, and the head of the chairman is saying, you know, I met this woman, and I asked her about this slide, and I queried her about the true answer, and she didn't know, therefore we should not accept her. Then the co-chair, which is a female, said, just wait a minute, I have here statistics that shows that men judges tend to question women more than they tend to question men. Would you have questioned the same doubts about the men candidate? And now you say what she was asking is causality. Was the reason that you questioned her the fact that she is a woman, or was the reason the fact that there was a mistake in the slide? And the chair of the committee started stuttering, he didn't know what to say, and she got the offer, the candidate. So, what I'm saying is that our notion of fairness often relies on causality, but causality is not something that we can measure. There is no way that we could measure whether he's questioning her dependent on the fact that she was a woman, or it was just a matter of the slides. Similarly, our notion of fairness depends on intention. Our notion of fairness depends on prejudice, where as in contrast with intention, you mean sometimes you have a prejudice that you're not even aware of, that it's unintended, it's implicit. So all those things are kind of play a role in our intuition of what is fair and not fair. But those are things that we cannot observe. So we cannot make regulations. We cannot make decisions about algorithms which are based on unobservable features. And I think, to me, this is one of the big reasons that we have such a difficulty with defining fairness, that we end up with definitions that contradict each other. Okay, so I want, I still have time, so I want to talk a little bit about, furthermore, about other aspects of fairness, so we can try to divide fairness notions into categories. So one category is whether they depend or not on unobservable data. Another category, another distinction or classification between notion of fairness is, do our notion of fairness depend on the true classification or not? You remember our first notion, demographic parity, did not depend on the true classification. We just said we want to accept the same percentage of black people as white people, regardless of whether they will succeed or not. So that's another categorization. So we can ask, is our notion of fairness depends only on observable data or depends on unobservable? Is our notion of fairness depend on the true classification or does not depend on the true classification, right? So statistical parity did not depend on true classification, the others do. We can also ask, does perfect prediction accuracy, does it suffice to count as fair? So assume that I'm predicting completely correctly. I release from jail only those that will not reoffend, and I keep in jail all those that would have reoffended. I'm completely accurate. Will this be considered fair? And some people will say that even that is not considered fair because this group is disadvantaged and this group is starting with, like if I say I accept to my program students only according to, I have a magic ball, whether they'll succeed or not, someone can tell me that's not fair to women because usually women are not doing computer science and we want to give them a better chance. So that's another kind of classification of our notion of fairness. Will perfect prediction be considered fair or not? The driving test is a good example of that, if you feel that there was something unfair. Okay, so statistical parity fails this requirement. Perfect prediction does not give you the same percentages in those groups. The other notions do give you judge it as fair if you are perfectly correct. But of course, in reality, when we make decisions, we don't know exactly what the true label is. So in the most notions that I talked about, except the demographic parity, if you knew the correct label and made no mistakes, it would be judged as fair. But of course, we are not there. So affirmative action really goes explicitly against this and say we should go against just judging by success rates because we want to make a change in society. So there's another question, whether our notion of fairness is aiming towards the dynamics, what will happen based on our decisions, or just trying to be fair at this point in time. Okay, so another very important question is, does unfairness be demonstrated on just a few points? So what do I mean? If the bank denied giving me a loan, so I go to the judge and claim the bank did me injustice. How can I prove my claim? So if we talk about individual fairness, I can say, oh, this other person has exactly the same features as me, but you gave them a loan, and you didn't give me the loan. That's unfair. I can show you unfairness based on a few points. There's this very famous thing of orchestras that they try to decide who to be accepted to the orchestra or not, and they were trying to do those tests without seeing the artist that is playing, and then they realized that the ratio of men and women that were accepted was different when they could not see if the artist was a man or a woman. So that you can prove based on just a few points. You can say, oh, this artist, you judged them the same as me when you didn't see if it's a man or a woman, but now that you saw, you make a different decision. So I can give you an argument against it based on just a few cases. But when we talk about group fairness, I cannot even do that. Because I cannot come to the judge, I don't have the statistics of the whole population. So that's another kind of distinction between notion of fairness. Can we prove unfairness based on just few examples? Anyway, so these are just to think about different considerations when we pick a notion of fairness, which of those criteria we wanted to satisfy and which we have to give up. We cannot satisfy all of them. Okay, so if we have time, I want to go into another important issue, which is the importance of data representation. So you see, when I want to decide if someone will get a loan or not, what information about this person am I asking? If I want to decide whether to give someone a job or not, I have a questionnaire. What do I ask in this questionnaire? Because my algorithm will depend on this feature or on the data representation that I use. So it turns out that even that is a complicated issue. So let me give you another famous story. The famous example is the story of Ben the Box. You can Google it.
It's okay.
Ben the Box. What's the Ben the Box? It turns out that when you wanted to get a position in a government position, in employment by the government, you had to fill a questionnaire, and one of the questions in the questionnaire was, were you ever convicted of a crime? Now, there came people who advocate for minority groups, and they say the chance of being convicted is much higher for black people than for white people. You should not base your decision on this box of where you convicted in the past. And indeed, in order to achieve this type of fairness, we know that the rate of convictions is higher for black people. So some states decided that this is called ban the box. They don't allow you to ask this question. They don't allow you to ask the applicant to tick this box. So they did this rule, and some states decided they are banning the box. And then in 2018, they did a search, and they found out is the paper is called The Unintended Consequences of Ban the Box. It's a paper that you can search and find. And it finds the employment rates dropped by 5% for black men in the age of 25% without college degree, once you did not ask, did you convict a crime? So the purpose was to increase the chance of black people to get a job. It decreased the chance of black people to get a job. How can we explain it? How can we explain the fact that once we didn't ask them if you were convicted, suddenly black people were getting less offers? The reason is that the algorithm now looks at this success rate among all the black people, rather than looking at success rates distinguishing the black people among to those that were convicted in the past and not convicted in the past. So if you're a black person that was not convicted in the past, when there was no this question, nobody could know that you are not convicted, and you will get the same treatment as someone who was convicted. So the overall effect statistically was against black people, although they were trying to help. Which comes to show us that the data representation is very important, and it has consequences that we are not intuitively aware of. We are trying to help. We change the data representation, we change the questionnaire, we hurt. We end up hurting. So it's a very important what is the data representation that is going to be fair, and there is a lot of literature on this notion of fairness of features. So this is, for example, it's a study on, you look at recommendation letters for faculty members, and you look at the question of whether the word brilliant appears in the letter or not. And you can see that this is different areas, and this is how often women's recommendation letters say brilliant, and how often men recommendation letters say brilliant. we see that across areas, across different disciplines, it's always the case that it's more likely to say brilliant. And it is also a real case. Well, my daughter was at the recruiting committee at CMU, and they were trying to give objective measures. So, for accepting or not. So they asked the faculties, what would be an objective measure for accepting a candidate? And many faculties says, if the recommendation letter said that they are brilliant, then you're more likely to accept them. But then they did this study and they found out that whether they say brilliant or not depends on whether you're a man or a woman. So it's very difficult to say which features should you take into account when you see, we were talking before about you have a predictor, you have a true answer, when is the predictor fair? But now I'm trying to see what is the predictor basing its decision on? Which features have what effect? So this leads me to this notion that also became popular by the same group of that introduced the individual fairness, which is fair representation. So we say that a data representation is fair if the set of features is such that based on those features, it guarantees that your decisions will be fair. And is it possible? So anyway, I mean, the question of saying whether based on those features your decision is guaranteed to be fair depends really on who is making the decision. Is the person who's making the decision malicious? If the person is trying to hurt females, then you'd rather not have the item whether you are female or not on the questionnaire. But if the person is just accuracy driven, maybe having more information will help them make better decisions. Or maybe they are fairness driven. Maybe the decision maker really wants to help women. Then you want to know, that we have grants that are for, we have another funny story. I'm in a committee now that has to decide on big grant by the Ontario government for professors from, what do you call it? Minority groups which are, how do you call it? They're visible minorities. So it is a grant especially for visible minorities. So people apply to this grant, and one of the people that we are now discussing the application is the chair of our department. The chair of our department is from Tunisia, and he is I'm applying for the grant because I'm a visible minority. You can see that I am dark skinned. But he's the chair of the department. He is not being treated anyway. So what I'm saying is the question of which features you should consider depends on what do you imagine is the motivation or what decision maker are you making. And even then, so when I talk about data representation that is going to be fair data representation, that will guarantee that the decision will be fair, it depends on who is making the decisions. Because if you are malicious, I want to give you as few information as possible. But if you are in other groups, I want to give you more information. But even then, even after we overcome this issue, we can ask, can there be a generic fair representation? That I want to accept you to a program in AI, and I want to accept students to a program in systems. Will the representation of students should be the same for both decisions to make sure that they are fair? So, or can we detect which features cause unfairness and which features not? So, anyway, we have a result with my students. We proved that you cannot do it. We proved, this is with the same student that I had the result that I showed last time, that for each of those notions of fairness, you cannot have a fair data representation. When the task changes, when I want to accept them to computer science rather than to accept them to a different program, to medical school, to be fair, I cannot use the same features. I cannot, well, once the task changes, then you cannot have features that will guarantee, not only just the task that changes, but also when the population that applies it changes. Because think of just demographic parity. I want the percentage that I accept among women will be the same as the percentage of women in the population. But what's the relevant population? The percentage of women that applied for the job, or the percentage of women in Ontario, or the percentage of women in Canada, or in the, or over else? I mean, what is the reference population? This is also changing according to different applications. So we cannot have a generic fair representation. This is becoming more and more subtle. The more we try to fix it, we can still show that you cannot have a representation that will guarantee fairness just by the representation. Just as we saw with this notion of brilliant, where you were trying to be fair, or with the bend the box when you were trying to be fair. We also could show, I think that we have it in the next slide, that for every fixed feature you cannot tell which way it will help fairness or help fairness, because it depends on the other feature in the representation. You cannot just say this single feature, brilliant, will help or criminal record, single feature, will it help or help? It depends on what are the other features. So we have results that show that this cannot be achieved. Yeah, I think I will just end with some discussion of what could be sources of unfairness. So sure, it could be inherent disparity between population. So we may want to use different decision rules for different populations. So for example, in order to accept students, we ask them if they did any voluntary work or community work during their high school. But in some neighborhoods, they don't have a chance to do community work. So by asking this, by using this feature, I'm discriminating against populations that came from an area where you didn't have this option of doing community work. So we may need to use different classifiers for different groups, and not use the same classifier for everyone. Another, there's an artifact of learned scoring rules. The data that we collected could be biased, and so it could be the unfairness, be the result of unfairness in the past, in labeling the data that we collected. And anyway, I mean, there are lots of reasons for unfairness. The question is difficult, and okay, it's less than time. What I wanted to convince you is it's a very difficult problem, and it's not just a problem that we can solve with mathematical tools. So, thank you.
So we'll take some questions. I have some.
Just one important thing that I forgot to put, that this is based on joint work with my previous student, who owner, and the current student, and yes, I can.
Yeah, I'd just like to say, this fairness issue in machine learning is a very, very important problem for machine learning developers and machine learning for industry that is trying to use machine learning. Fairness is probably the most important thing, and the Korean government is trying very, very hard to make all the machine learning algorithms that's going to be used publicly to be fair. So this is a very important issue. So while people are thinking about a question, I'd like to pose a question to you. You mentioned, actually there's two questions. One regarding features. You said, one, if you disregard a particular feature, that might make it actually
have an effect which is opposite to what you predicted.
Now, we can make the features independent. there are features, the features are probably correlated in some way. If you can make them independent and then cross out certain features, would that help? That's my first question. Okay. My second question is, you had different incompatible, I know that there are thousands, not thousands, but many, many different criteria for fairness. Probably you used three, over 30, let's say, I know. And many of them are incompatible. Is it possible to have a linear combination of them in a certain way? So it's like you have one and it's playing against the other like a regularizer, because the regularizer are usually going against accuracy or loss function.
Anyway, I mean,
yes. So those are two of my questions.
Oh, okay. So first of all, making the features independent. Independence is a statistical notion. It depends on the population. So it could be that your features are independent in one population, and then that it independent among the same features will be independent in a population of students that apply for a CS program, but they will not be independent in the population of students that apply to matrix. And it could be that they will be independent in the students that come from Korea, and they will not be independent in the students that come from Vietnam. Because in Vietnam you have more correlations between those features and what they do. So we don't have a generic answer to this independence. This independence is a subtle issue. It's statistical, depends on the underlying population. Underlying population is changing from one question that we try to solve. Now, for the other linear combination, I mean,
linear or some type of combination.
Yeah, I mean, basically my belief is that this is a very easy way to write things. Show that any linear combination is inconsistent with any other linear combination. I'm sure that it's going to be easy to show. But once you pick your coefficients of the different measures, and you will pick different coefficients, the two things will contradict each other. I mean, if you want to just write an easy paper, try it. I think it will take you have to read the papers that show that the two notions are incompatible with each other and adjust it to a linear combination.
Yes, please.
Thank you for your talk. I really enjoyed your talk because it's very philosophical. It reminds me kind of like the discussion between David Hume and Immanuel Kant. And David Hume said, knowing the causality from experiences is possible. Immanuel Kant, actually, from the understanding of the duality, causality is possible. So this is very similar thing to the philosophy. And the question is, you mentioned that causality is something unobjective, something you can't really figure out. But we have, I guess, mathematical definition of causality.
The mathematical definition of causality depends on very strong assumptions. You have a graph of features. You assume that no external features have any effect. You assume that this is completely unrealistic. I mean, I already told there is a very nice lecture by Richard Feynman. Richard Feynman is a famous.
Feynman.
Very famous. This is the lecture in which he is discussing, he is interviewed by someone, and this person asks him a question about why does magnetism do such a thing? And Feynman just stops and says, oh, why? You ask me a why question. It's a very interesting question. You know, my aunt ended up in the hospital. You can ask me, why did she end up in the hospital? And I will tell you, she ended up in the hospital because she sleeps on ice. But you can tell me, oh, that's not the reason. Why is ice slippery? And why, if she slipped on ice, did she break a bone? Why sleeping on ice causes? And why, if she slipped on ice and broke a bone, did she end up in the hospital? And he goes into showing the absurdity of asking why. I mean, there are so many, and the answers of counterfactual is also kind of, it holds in the extreme artificial cases. But if I want to know if a parachute saves you when you jump from a plane, then I want to check the counterfactual. So I have to take two similar people and have one of them jump from the plane with a parachute and the other without the parachute and see if the outcome is different. But I'm not going to do such an experiment. So, and in many cases, you ask me, you know, my knee hurts, is it because of my age? So, can you take a replica of me? Would it be similar in every other aspect, but just be younger and see if the knee hurts or not? I think that causality is a very kind of, is a silver bullet. Once we understand causality, everything, many things could be solved. But we have to realize that we are not scratching the surface of understanding causality. And all this Yuda Perl book and graphs and everything, it's a mathematical game that is detached from reality. So, yes?
I have a question. Basically, if we already prove that notions of fairness are impossible, is it still a mathematical problem or just a regulation problem now? Because it seems like we only have to make choices now about which notion of fairness we're going to use and not waiting for more research. Because anyway,
Right. So that is a very good question. And I think that in part you're right. But we have the difficult task of explaining to the laws that make the regulations what is the difference between the two definitions. You have to explain to them in the situation that says, we know, in my situation, do I want demographic parity or do I want equal odds? And it is a very, even for us, I mean, we are mathematically educated, and if I tell you that for acceptance to university, we want to use one measure or another, what will be more fair, you will be passed. You will not have a clear answer. So I think we have here, you're right. I mean, it's a moral decision, it's not a mathematical decision, but the mathematics should give you a tool to clarify your thoughts, to understand the consequences of the fact that you chose one definition or the other, and you need to choose a definition. Because, as you were saying, I mean, the Korean government is trying to require fairness. So if you require fairness, so you have to be able to go to court and say, I've been treated unfairly. Now we have to convince the judge. And we cannot avoid it, but one of our big tasks, I think, is trying to understand things better ourselves and then be able to convey this understanding to people who are less mathematically educated, but they make decisions. And that's very good.
okay, so more into communication then.
Yeah, I mean, there are many cases that you see that judge decisions are based on ignorance in statistics. There is this famous case that you know about in Netherlands that was a nurse that was convicted based on statistics that she's murdering patients because they compared the ratio of patients that died when she was doing the shift to the ratio of patients that passed away when other nurses were doing it. And they convicted her just based on those ratios. And then Peter Grunwald, the famous Oscar scientist in Netherlands, he managed to prove that they didn't understand the statistics. And the court, that was after she spent a few years in prison. So the judges, I mean, the task of, first of all, it's so difficult for us ourselves to understand. It is even more difficult to be able to convey it to judges or to regulators.
Follow-up question, do you think that either Korea or even the EU will take the risk actually to define the straight thresholds at which they take fairness decision or taking moral decision basically? Because right now, for example, the EU framework has so far been defined to be very loose so that it can encompass everything, but actually as an engineer, it is not applicable. I mean, it means nothing right now at the time, but it means nothing.
So
in
we
terms of functionality.
have workshops on fairness. I was running a workshop in Berkeley in the Simons Institute in which we invited lawyers also to give us advice on what should pass in court. And the advice that we got from the lawyers was make your decisions process as vague as possible. The more vague it is, the more difficult it will be to sue. So, yeah, I don't have a good answer. But I also agree that it's important to require facts, to require transparency, to require interpretability. It's a good direction to go for, but I think that the society is not aware of how complex those issues are and how little understanding they have about the areas in which they make decisions. But the direction is definitely needed.
So you think that societies will actually decide on these questions or not?
What?
Will societies make a decision on these questions or keep it loose?
There are moving towards making decisions. I mean, that's the nature of regulators, that's the nature of judges. I mean, I'm not, and sometimes they don't have a choice. I mean, the judge cannot say, oh, in this case, I cannot decide, so you will not be free, but you will not be in prison, because I cannot decide. So I think our role is to try to clarify it more and more. And you know, what I was trying to do here is to show you that even to ourselves, we're not clear. Before we can move over and try to help others understand.
So is the future of legal defense actually just collaborating with a statistician to prove perhaps that a model is on average unfair against your particular group?
The future of what?
Legal defense.
The future of legal, I would hope that legal defense will move into more collaborations with people that understand statistics. But right now, I mean, we really rely on understanding of juries or judges, and they have a very poor understanding.
One more question, yes. Thank you very much, my name is Shai. Thank you for the lecture. And we talk about a lot of examples and theories today, and it becomes more and more complicated. So in my short thought, it seems like we cannot eventually meet the value of fairness in their AI tool. In specific domain, I'm talking about general representation. So my question is that it could be a comprehensive question, but do you think the AI tool can be fair even in a specific domain? I just want to hear your thoughts on this.
Yeah, so, you know, one direction is clearly that the more accurate you are, the closer you get to fairness, in our basic understanding of fairness. So, improving the accuracy of predictions, and, you know, if I accept students, if and only if they are going to succeed in the program, then I feel fair. But we will always have errors, and the question is how the errors spread between groups. And now I think what we can do is try to understand sources of unfairness. We can say a source of unfairness is that we don't have enough data for this group. Or we can say the source of unfairness is that our training data was biased. Those are things that we can investigate. And, or using active learning to try to say, oh, I need more information about this specific case. Or the active learning can also go in a different direction. Usually when we talk about active learning, it tells me I'm trying to query a point for which I didn't have the data. But active learning, think of it in medicine. I mean, I have a patient, I cannot decide whether the patient should do surgery or not. It's not that I'm actively checking another patient, but I'm doing more tests to this patient. I'm now investing more resources and getting more features about this individual because I realize that for those individuals, my data is not giving me good enough information. So questions of, having kind of a hierarchy. I mean, I can make decisions cheaply, and I can realize that in this case, I'm prone to misprecision, I'm prone to unfairness. So in those cases, I should invest more into understanding the situation before making a decision.
Okay, we'll take one more question. It's a very controversial topic. And
No,
we can go on.
I really enjoy discussing it and getting insights from the questions, yes.
Thank you for your good presentation. My question is, what is the goal of fairness? If we make some fair model, then we can minimize some.
Yeah, well, now you're going to be tautological, right? If we make it fair, we minimize unfairness. Yeah, I mean, I think that, it's an important question. What is our goal? What are we trying to achieve? And often the answer is that we are trying to create some social change. And for that, we need to be able to understand what will be the next step, consequences of the decision we make now. And this is an area in which we are even less knowledgeable than in trying to decide if our current decisions. Right? If I now, there is the Turing Award. And the most important award in computer science is the Turing Award. It's not Nobel Prize. So now they decided, they looked at the data and they saw that much fewer women got a Turing Award than men. So they made a decision recent 2 years ago or a year ago that from now on the Turing Award will always be one for men.
What?
But now the effect will be that when a female gets a Turing Award, you will say, oh, it's not that she's such a great scientist, she got it because she's a woman. I mean, you were trying to rectify a problem, but so...
Devalue
right. I mean, so the questions of what are our goals and what is our moral compass are very difficult and are beyond computer science, but we have to think about it. We cannot just say, we are geeks, we are mathematicians, we just look at numbers, we don't worry about such questions. I think that's irresponsible to take such a
Okay, so we will wrap up here, and I really would like, I've over the week, I've got to know our speaker, Shai, Ben, David, and wonderful man. He's inspired me, and it's a real great honor to have him here. Let's give him a